Have you ever wondered why quantum mechanics, the theory that explains the smallest particles, fails to explain gravity, the force that holds the universe together? Quantum mechanics, a marvel of 20th century science, offers a profound understanding of the atomic and subatomic world. It's the key that unlocks the bizarre and often paradoxical behavior of particles at this inconceivably small scale. On the other hand, we have gravity, a colossal force that we're all too familiar with. It's the invisible hand that keeps our feet on the ground and our planet in orbit. It's the force that shapes galaxies and directs the cosmic ballet of celestial bodies. Yet for all their individual brilliance, these two theories seem like estranged dancers, unable to find common ground. Quantum mechanics and gravity, two vital pieces of the cosmic puzzle, remain stubbornly incompatible. So we've got two theories, each beautifully explaining a part of our universe. But why can't they come together? Quantum mechanics at its core is a theory of the microcosm. It's a fascinating world of subatomic particles where rules that govern our daily lives seem to lose their grip. Quantum mechanics introduces us to principles that seem almost fantastical: superposition and entanglement. Superposition, for instance, is the idea that a particle can be in multiple states at once, only settling into a definite state once observed. Then there's entanglement, the mysterious phenomenon where pairs or groups of particles interact in such a way that the state of each particle cannot be described independently of the others, even when separated by vast distances. Quantum mechanics has been spectacularly successful in predicting and explaining the behavior of these tiny particles. It's been instrumental in the development of technologies we now take for granted, like lasers and semiconductors. Quantum mechanics gives us a perfect picture of the microcosm, but what happens when we try to apply it to the macrocosm? Gravity, on the other hand, is a theory of the macrocosm. It's a force that we experience every day, yet rarely give a second thought. This invisible power is what keeps our feet firmly on the ground and the planets in their orbits. It's described by Einstein's theory of general relativity as the curvature of space-time caused by mass and energy. The more mass an object has, the more it bends the space-time around it, and this bending is what we perceive as gravity. It's the reason why an apple falls from a tree and why the moon orbits the Earth. It's also crucial in maintaining the structure of the universe. Without gravity, stars and galaxies wouldn't form, and the cosmos would be a chaotic mess of particles. In essence, gravity is the great cosmic glue, binding everything from the smallest pebble to the largest star. Gravity holds our universe together, but it remains a mystery in the quantum world. So, why do quantum mechanics and gravity contradict each other? Well, the trouble arises when we try to apply the principles of quantum mechanics to gravity. Quantum mechanics, the theory that explains the behavior of particles at the smallest scales, works beautifully for three of the four fundamental forces of nature: electromagnetism, and the strong and weak nuclear forces. But gravity, the force that holds the universe together, simply doesn't fit into the quantum framework. Now, the scientific community isn't one to back down from a challenge. Researchers are tirelessly exploring theories like string theory, which proposes that everything in the universe is composed of tiny, vibrating strings, and loop quantum gravity, which suggests that space itself is quantized. These theories, while still under development, offer tantalizing glimpses into a future where quantum mechanics and gravity might coexist. Despite the seeming incompatibility, the quest to reconcile quantum mechanics and gravity continues, reminding us that every unanswered question is an opportunity for discovery.